This is another fire centre pop-up seminar that we're having. We're having, on occasions when we're having interesting people visiting the state, we're really pleased to have Michael-Shawn Fletcher from the University of Melbourne. Michael's got a strong connection to Tasmania. He did his PhD in Southwest Tasmania and palynology. He's maintained an interest in Tasmania land cover change, but he's also broadening his interests and working in Northern Australia, but he also worked abroad in Chile. So he brings a really interesting perspective, time perspective, but also, I think, intellectual perspective. Particularly interested in the Indigenous perspective, given his fact that he is of Indigenous descent, which is, I think, a very significant fact that we've got a high calibre researcher who's thinking about the legacy of 40,000, 60,000 years of human landscape burning. So I'll hand over to Michael.
Thanks, David.
Good to have you here.
Yep, no worries. Right, thanks for having me. So, yeah, as Dave said, I've been working a long time in Tasmania on the long-term landscape history. I guess I'll touch a little bit on the Indigenous stuff, but this is more centred around ecology. But my thinking is always framed around the role of people and the influence people have in landscapes. So we'll see how we go. I've got a fair bit to get through. I generally jam these things full because I think it's important to set up my intellectual universe, if you like, that I operate in, and then get to my conclusions, and then people can ask questions about any of it if they like. So what's the problem? I guess we have a problem here that there's an increase in landscape scale fires that are threatening the existence of fire-sensitive plant communities across the Southern Hemisphere. This is due to climate change and due to the invasion of continental Europeans, and I say British because now they haven't quite Brexited, but they're not European anymore, invading the Southern Hemisphere and other places, changing the way that landscapes were managed. And the other compounding factor is that we really have little to no understanding of what factors underpin the resilience of many of these systems, especially the long-lived ones, with life cycles that count into the thousands of years. We have no real appreciation of what drives them. And a case in point, I'm picking on a particular community that is found in a few places in Tasmania today. It was much more widespread 10,000 years ago or so, are the Atrataxis nothofagus montane rainforests. That's what I'm defining as a montane rainforest in this talk. So there's been a lot of work on the nature of fire regime change in the post-British invasion period. Initial really big landscape scale fires early on, and some anomalously zero reported fires here anyway, and really large scale fires punctuating the period of British occupation of Tasmania. And I guess the most recent and part of what's driving a bit of David's work now, and something that we've come together over, are the big Lake Mackenzie, or the 2016 fires. The bigger ones were actually on the west coast, or towards the west coast, but the ones that captured people's imaginations are these ones around Lake Mackenzie that threatened, and in some cases wiped out, some of these Atrataxis systems, Atrataxis sphagnum systems. Focusing in on the Lake Mackenzie, just to provide a bit of a context, they've cost a lot of money, whether that be in the triage or in the attempts to contain these fires. And the latest spate of fires, I haven't seen the figures, but I imagine they're just as enormous. A lot of money goes into these things, and we see destruction, if you like, and this is all time dependent and time context, of these really endangered or super fire sensitive plant systems. For those who don't know, which I doubt many of you don't, this is a pencil pine. This is kind of the effects of post-Lake Mackenzie fires. There are these evidences of landscape scale fires all across the landscape, these sort of tombstones, if you like. It's almost like the Normandy beaches where you walk in and there's all those tombstones. In many places there are just thousands upon thousands of dead stags in the landscape, that most of which correspond, I think these are the 1930s, in the southern ranges, the Brotnella rise. Post-date the arrival of British into Tasmania. And some various mapping attempts, and I think the estimate now ranges, I was corrected by John Marsden Smedley the last time I was here, I've always thought it was around about a third. He seems to think it could be anywhere up to about a half of the extant areas of Athrataxis, extant at British arrival, British invasion, have been wiped out in the post-British period due to landscape-scale fires. So we're dealing with a real problem. So as an indication of how little we know, some modelling work, and models are as good as the universe that they're created in, but they give us an indication on how systems work. With this particular model, 3 scenarios of fire suppression were run over 1,000 years. Okay, and this is in order of fire suppression, so not much fire suppression all the way through to maximum fire suppression in this model, which is 90%. The blue line here is what we're interested in, the Athrataxis. Starting off with this particular area around Cradle Mountain, how much was in the landscape at the time, in the modern example, running it for 1,000 years, even under maximum suppression, which you think would favour a hyperfire sensitive species, they virtually peter out. Yeah? So we really know very little about why there was so much of this stuff in the landscape in the first place. Yeah? And in my thinking and working with other people, I think one thing we're missing here is, or one thing we're not doing, is allowing the people who are living in this landscape to be intelligent, if you like. And some agent-based modelling by George Perry and others, there's a big debate over how Maoris could have possibly devegetated or deforested the South Island of New Zealand in the time that they did. It just didn't make any ecological sense until they developed models, or they gave people intelligence in models, changing where things were burnt, targeting areas that were more probable to get a good return. And it's very easy then, once you provide intelligence to humans, to have radical change that we might not expect in otherwise situations. So this is just more wrapping up the paucity of knowledge around these systems and what the long-term management was of them, why they're there today, what the determinants are, the requirements are for their maintenance, if that's what we want to do. This is not idiosyncratic to Tasmania. The similar problems happen everywhere across the southern hemisphere. This is a cypress pine in Nothofagus dominant rainforest that has suffered massively from post-Spanish invasion fires. Oh, down here it might have even been the Germans. So, what's the bigger context? And there's people here, mate, Greg Jordan could give you a better sum up of this. But Australia's been getting drier over geological time. As we separated from Antarctica, drifted north, the Quaternary glaciation set in, we got further drying, if you like. Australia's just been getting drier and drier and drier. This has forced mesic or rainforest vegetation out to the edges where they can pick up orographic moisture. And this is the distribution of mesic or rainforests today. We know from the geological record they were found pretty much all over the Australian continent, especially Nothofagus and things like that. Another factor that we need to think about in the modern landscape and how it influences the dynamics of vegetation is species invasion or the way that species alter ecosystems. And the key player here in this context is eucalyptus and how it can transform ecosystems. In this model of Kill Thy Neighbour, which was developed in the 90s, it's received a bit of a battering and has various supporters and critiquers. Sort of highlights what flammable plants can do in non-flammable systems. They can get in and transform ecosystems into their favour, causing the loss of fire-sensitive ecosystems and the spread of fire-adapted ecosystems. And then there's a whole complex of vegetation, fire, climate dynamics that I won't go into here. But in Tasmania, some of the work we've done on how fires link to climate, okay, very relevant for thinking about how we're going to manage systems into the future. Here's obviously Tasmania here. The southern westerly winds, which encircled Antarctica, they move north and south in this rhythm called the southern angular mode. Some work we've done on fire occurrence and the southern annular mode shows, and this is just a significance test if you like, a superposed epoch analysis that shows there's a significant relationship if you have a positive SAM year, so a drying of Tasmania in relationship to the movement of these westerlies, and fire occurrence. Okay, drier, the year after you're going to get fire. And the opposite is true. When they move further north during negative SAM modes, when Tasmania's wetter, there's a significant decrease in fire in the following year. So the antecedent rainfall related to SAM is important. And then if we compile charcoal records from, I think this was 11 sites across here, synthesise them, we can see this is a proxy of SAM through time. We can see a really tight coherence between long-term fire activity and what SAM is doing, or southern annular mode, so what the westerlies are doing. And you can see that we've, over the last 1,000 years, we're in a period of more burning than there has been in the last 1,000 years on that historical context. And if we zoom out, some work we did subsequent to that with a few more sites, over the Holocene, or the current interglacial, 12,000 years, we are now in a period of more fire in the landscape than there has been over that entire period. Okay? We went through the early Holocene, straight out of the last ice age, more fire, less, so it was quite wet. This sort of variable, steady increase to peak values of the last 12,000 years. And we see from Rebecca's work last year, I think it was, we see that what potentially the culmination of this is, more fire in the landscape, extreme weather events here, anomalously low rainfall, anomalously high temperature, is associated with a catastrophic loss, if you like, or a catastrophic event that threatens these fire-sensitive ecosystems. So we're in a potentially, we're definitely in uncharted territory in terms of how much fire is in the landscape, and it seems as though we're in uncharted territory about how extreme or how variable the weather is as well. So how, we're thinking about managing these systems in the context of this new baseline, if you like. Then, hope you don't all go and drive the car off the bridge after all this, because it doesn't sound that great, but we've done some modelling recently, and David's involved in this. The take-home message here is the red periods into the future, the blue periods, the baseline, lightning-induced fires in the southern hemisphere under various models, under various SAM, IOD, El Nino temperature, are predicted to increase. Okay, so we're going to get more lightning strike fires. This is actually, incidentally, we've just developed two really excellent, more than 200,000 year records from the west coast, Lake Selina and Darwin Crater. There's a really interesting relationship between rapidly changing climate and peaks in charcoal. It seems like when climate's changing rapidly in that part of Tasmania, you're getting more fire, whether people are around or not. So something to do with atmospheric instability through those periods, which is what we're seeing now. So what does this mean? We know even under lower sea levels, there's really not much room to go. So, the future doesn't look that great. And it's sort of, at various times I've been wanting to sort of pick up on the goodbye Gondwana theme, but I stick to my guns and think about positively how we can get at this. So setting up my intellectual universe, I want to go through this relatively quickly because some of you may not, I really don't know how around this stuff you are. So this is just an intellectual paradigm I'm going to run through here. David and I had an interesting conversation last week about how real these things are or not, but they're useful in terms of how we generate predictions or how we can, some of the things we expect to see if certain things are happening. I'll explain what I mean soon. Okay, so there's this notion of stable states, okay, stabilising feedbacks that in some systems, not all, you can have two ecosystems, if you like, okay, two different types of ecosystems existing either side by side or under the same set of conditions, and they are there because they have these stabilising feedbacks. In flammable vegetation, you might have flammable vegetation growing that produces more fire then they just come back in and dominate, and you get this fire trap, if you like. And the opposite can be true in a rainforest. Okay, rainforests are less flammable. They shade out these more light-requiring species. They create a microclimate that's more damp, all these sorts of things, and they can essentially hold out fire in anything but extreme situations. And there are various overlays on this. There's nutrients, there's waterlogging, all these sorts of things that feed into these stable cycle feedbacks. So in terms of a stability landscape, we have a state, if you like, under a set of conditions. Yeah, so it can be anything. Let's call it fire or call it climate or something, just a set of environmental parameters. You can have an ecosystem existing in one of two states. Okay, let's say up here we have rainforest, here we have fire-adapted vegetation or non-forest. Under a set of conditions, it can persist relatively stably, but under this circumstance, it might just get too wet and fire can't occur, and you might get a rainforest move in, and vice versa. It might get too dry and the rainforest collapses. Where these two overlap in sense of environmental conditions is considered a bistable zone, yeah, and that's where you get these alternative stable states. An ecosystem can toggle between them, and they're really interesting. Because we don't know, the classic example is eutrophication of lakes. I mean, you can have a lake at the bottom of your field, pump phosphorus in there all you want, did it for generations of farming, then overnight it might eutrophy. Or you might get thousands of dead fish in the Darling River. Yeah? That's a combination of a series of effects and a threshold crossed. We want to know whether these things can toggle or not. And often they're unexpected when they do flip. And then we have this kind of hypothetical threshold between the two, and I'll explain how that moves in. So if we sort of cut a cross-section through this, you get to these things called basins of attraction. In this situation, forest is the only feasible state in this intellectual exercise. You can kick it around, you can knock it, you can burn it, you can do whatever, but conditions are so suited to that returning that it returns into forest. It's got a deep, resilient basin. If you're sitting here, there's albeit small, there's a possibility that you can force. It's a long distance between the threshold, but you can force this system out into this non-forest system. Yeah? Here, it's a bit more equal. You can kick the ball out, vice versa, either way. Okay, and this is how these stability landscapes. Over here, rainforests will never form. It's just either too dry, too much fire, whatever the environmental parameters are that you're thinking. So this intellectual exercise is useful. I mean, no one is arguing there's actually ethereal basins out there that these things are living in, but they're useful in terms of getting at things like resilience and picking up early warning signals for things that are going to change. If you imagine your states all the way over here, you only have to go comparative to over here. To get it into a non-forest, you have to do a lot of work. Whereas if your state is sitting over here, your ecosystem, you only have to give it a small kick and you're gone. So the amount of effort needed to move this system is different in these two areas. There's a difference of resilience here. Yeah? Okay, and this can be in terms of changing conditions a bit more or giving it a kind of a kick, burning it or something like that, or disturbing it, perturbing it. And then there's been a lot of work on this. We can sort of hypothesise, if you like, what some early warning indicators might be. What are some symptoms of a system that is of low resilience? And it turns out one of the key ones is they're slower in recovery. Okay, they're more lethargic, if you like. If you kick this ball, it rolls up the basin, it's steep, it bounces back really quick, and this sort of cluster of state versus state time plus one are tight together. You've got a really tight, resilient system. Yeah. If the basin's more sloppy, more loose, the ball takes a little bit more time to roll around, and you get this kind of really variable spreading system. So we can start to investigate whether these are actually there. And we did this for Lake Vera over the last 1,000 years. This is the diatom community. We identified a point where there's a clear shift, ecosystem shift. We thought it was in response to fires. Read the paper if you want to get into it. But what was associated with this shift? It turns out that variance around this sort of modelled mean increases prior to the shift, and so does the rate of change. The system's becoming more variable. It's bouncing around more just prior to an ecosystem shift. We also did it to the pollen. We looked at the pollen. Now, it's still a rainforest, if you like, around Lake Vera, but there's a little fringe on the downwind side, that whole slope on the eastern side that's facing the west has got Eucalyptus delegatensis through, I think. So it's, you could argue that it's about to transition. Really stable system. It's starting to get really variable. Yeah. Okay. Variability shot up. Rate of change is shot up. So you might argue that this rainforest system is of low resilience. Yeah. It is on the point, or it is approaching what in the sort of dramatic terms is called a catastrophic bifurcation, or a tipping point, or whatever you want to call them. Yeah? So these metrics might have some use in anticipating critical transitions. Okay, so what about this montane rainforest? Preaching and converted here, 2 species. The point I want you to take out of this is they are slow-growing, long-lived, hyperfire sensitive. Yeah? Really, really long-lived. Okay? Phenomenally long-lived. Slow-growing, hyperfire sensitive, really poor dispersers. These things are really maladapted, if you like, to change, to big, fast change. Okay, in the landscape, we have topographic complexity. We have a dominance of fire-promoting vegetation, eucalyptus and other sclerophyll species. And we have a cool, humid climate. Okay. So in thinking about what might be the determinants, before I take us back in time, of what the resilience are once setting up my intellectual universe, i.e. how can we manage this endangered community into the future given that the hyperfire sensitivity, the climate trends, the remoteness, and the topographic and financial challenges to fire control. Okay, just to ram home the slow dispersal thing, this is something from Jamie, 1984. I think the estimate was it only disperses, twice the height of the parent tree or something like that. Really, really slow dispersal of this particular species. This is Cuprossoides, this is pencil pine. Some of the work we've done on Selaginoides shows that after a fire, this is a cross-correlation analysis, after a fire, you don't get a significant increase in pollen records until around 800 years after the fire. Okay? It is slow once it's removed from an area to get back in, and slow recovery. Yeah? So it's a slow dispersal, slow-growing, hyperfire-sensitive species. That leads me into really interesting work from Toledo et al. In Nature, Ecology and Evolution, where they're teasing out what the effect of climate change is on North American ecosystems, where things can migrate north and south. Yeah, here we have an analogue going up and down a slope in north and south in response to temperature change. And they develop these ideas of extinction debt, or they further these ideas of extinction debt that have been hanging around the literature, and colonisation credit. And then another person, who I can never pronounce her name, Lahole, develops this idea of relaxation time. And what it means is that if you have a slow-growing, poorly dispersed, long-lived species, they're going to be slow to move into new territory, and they're going to be slow to move out of old territory. They've got a long relaxation time. And that influences how they respond to disturbance. Okay, so you get these extinction debt in area. Well, we don't know. One thing they didn't do was try and understand how these things respond to disturbance. They're showing that at the base of some of these species, okay, these slower growing, betula and things like that, populus, the trees, there's a long tail, there's an extinction debt. There's plants out of equilibrium with climate. Yeah? But they don't take up the new area very readily because they're too slow. So they're being squeezed, yeah, like a pimple. If they don't keep up with the movement, then there's a chance that you're going to have large areas of population out of equilibrium with climate. And my interest being from a place where fire is so common is how did that influence the resilience of these things? And here you have species that are really good at the high, fast species, if you like, or fast earth species. So climate change promotes a disequilibrium between species and climate. This is exacerbated in long-lived, poorly dispersed species, further exacerbated in topographically complex landscapes that provide areas of micro-refugia where things can hang around a bit more. Okay, they're almost leading you down the garden path, if you like. How do long relaxation times and resulting extinction debt influence the response to disturbance is a key question that I'm trying to tackle here. So then, setting up some more context, what happened in the climate in Tasmania, I'll just go through this really quickly. There was a shift from a low frequency variation, multi-millennial scale over the prior to 5,000 years, where we had that dryish early Holocene, really wet mid-Holocene, and then it's become variable as ENSOs kicked in, yeah, after about 5,000 years ago. Important for this is it was a stable climate and wet between 8 and 5,000 years ago, increasing variability after 5,000 years ago as ENSOs switched on. Before then it was really quiet. Okay, this is a proxy for El Nino events. Really quiet through this period here, 12,000 years ago to present. Quiet and ramping up, and things are getting more variable. That's the climate story that's, you know, a really well-trodden story now, so we're confident with that. How does that influence montane rainforest? So here's a site from Lake Osborne on the Harts Range, 6,000 years to 0,000 years. Cupressaceae pollen, so Athrotaxis pollen. These grey bars are significant charcoal peaks, fire events. And you can see a negative excursion, bang, 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 every time there's a fire, okay, at this site. And this is that El Nino curve again. Every time there's lots of El Ninos, boom, 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 you're getting a fire here, yeah? And we've done a bit more sophisticated modelling from a whole series of sites we have across both the Broke-Miller Rise and the Harts Range now. And you get this really cool kind of, I don't know, you see, probably would have seen these printed on T-shirts at Woodstock. But this is 12,000 years ago to present. This is a wavelet coherence plot. Essentially, it's taking two time series. It's analysing their relationship in time to each other. Okay, and if there's a significant relationship in time, you get a red colour. Okay, and the direction of the arrow says whether one's leading or lagging the other. The important thing is here to note that once ENSO switches on, there is a really significant relationship between what Cupressaceae pollen does and what ENSO does. Yeah? And its relationship is through fire. Yeah? ENSO promotes fire, you get decreases in Cupressaceae. So ENSO is really, really powerful in this neck of the woods, down there in the southern ranges. Just highlighting that climate vegetation link. Species invasion, some more paleo work that we've done. Lake Vera, here's that wet sclerophyll forest, the Delgatensis, I think it is, or was it Nitida there? Has anyone got that down? No? I'll just make it up then. And this is rainforest. Okay, so your king billies all the way up here. There's Largostrobus everywhere here. You know, really your stuff that the greenies get off on. And yeah, this is that bit area where I think you're starting to see this system moving into a toggling space, and you know, a couple more fires, boom, see you later. How is eucalyptus involved in this? We've got a beautiful long record here. I don't want you to get into it. This is a pollen record. People always get scared of them. The time runs up here. Okay, these are all different species, and this is, you know, what they were doing 18,000 years ago, right through to the present. Yeah, I don't want you to dig into what this is doing. I've provided more of a summary plot here. You can see lots of fire at the end of the last ice age, lots of eucalypt in the landscape. Eucalypt disappears, rainforest is boom. Then right at the end here, after about 2,000 years ago, eucalypts are moving in. The ecosystem changing. This is an ordination axis of the principal ordination axis. Things are moving around. Rate of change is banging up. This is that resilience indicators I'm telling you about, and eucalypts increase. So we did a time series shot at this, and it turns out, I don't want you to get this, I basically did this because I liked the name. It's called Granger causality. Have anyone heard of Granger causality? Basically, they did the test on chickens and eggs. You think they were trying to prove what came first, chicken and egg, but it was actually egg production versus number of chickens, so it's not really as philosophical as it sounds. But in the late Pleistocene, a term here, at the end of the last ice age, charcoal always leads eucalypts. So it's following this pattern of burning is promoting eucalypts in this landscape. Yeah. Here, the data suggests, we've got to unpack this more, okay, here, in that last bit here, through the Holocene, the recent period, it seems like eucalypt is leading charcoal. Eucalypts are creating the charcoal, or they're driving the fire regime. Yeah? So we may be seeing evidence of eucalyptus being an ecological engineer in that site, in concert with the background fire activity there's always been in Tasmania since humans have arrived. So then there's topography, and a lot of work that Sam Wood, who you all probably know, and David have done. We know that there are things called topographic fire refugia, and that rainforests hang in them because they provide protection from fire. So that's the world, if you like, according to me, according to other people really. So how do we test these in the context of montane rainforest? So we've performed a couple of things. we've performed species distribution modelling, neoecology, and we've tried to merge this with paleoecology, past ecology, from a whole series of lake sediments that we've accumulated over the last decade. The species distribution modelling we've done is through Maxent, and we've modelled based on extant co-occurrences of Nothofagus and Atrataxis, and projected the likelihood based on climate alone, climate variables alone, of finding that community in the landscape today. Irrespective of biogeographic things, irrespective of previous disturbances, just give us a map of where the climate's suitable, irrespective of soils, all this sort of stuff, yeah? It's a climate map. So it gets at that, helps us get at that thing about, does climate change or is climate influential over the resilience, you know? Then it gets at that extinction debt problem that I highlighted. Are areas of extinction debt more prone to or less resilient than areas in that kind of the nice ideal hump? Bioclim variables. It's just been published in Global Change Biology. A good performance of the model doesn't really tell you anything about its reliability. It's just saying the model's performing well. Total precipitation seems to be the biggest player of the variables, followed by mean temperature of the warmest quarter, so warm season temperature. Okay, so this gives us a climate space map. Now, I was interested in doing this. I encouraged my remarkably productive PhD student, Michaela, who's finished now and is off in Nottingham, to do this because I was inspired by this Hirota paper on the resilience of Amazonian rainforests, where they used species distribution modelling, used moisture only, predictive moisture, and what they found is that this was inspired for them by areas where they've cut parts of the Amazon rainforest down. Now they're trying to revegetate it, and it just won't grow back. It's too dry. What? It was here before. Why is it too dry? And they have found that the likelihood of rainfall as a function only of finding rainforest in the Amazon is lower, obviously, as you move from this equatorial belt. But large areas have a less than a 50% chance of finding rainforest areas as a function of rainfall alone. They're probably a historical effect. They've been there for a long time. Climate's changed. And what they've hypothesised in this paper is that the extra moisture is actually being provided by transpiration from the forest itself. Yeah? So it's buffering itself. And they infer this in terms of resilience of this forest. So this inspired me here. Okay, is this climate map of Atrataxis and Nothofagus a similar resilience map? So we picked 3 sites. Sorry, a bit blurry here, but there's Owen Tarn, which I think actually has a different name. It's that one up on top of Mount Owen, Lake Osborne and Lake Wilkes. Lake Osborne, the Harts Range, Lake Wilkes is that one just above Dove. The scores, the Maxent probability scores, I'm not sure if it's in this. Yep. Okay, here at Lake Wilkes it's 0.82, so 80% probability of finding it as a function of climate, what we might call a high resilience or really suitable climate. The others are 0.3 and 0.4, okay, so lower than the 50% cutoff. And you see here, and this is the pollen records, this is the montane, the combined Atrataxis and Nothofagus, you see, they were there for the last 7,000 years. Unfortunately, time runs the other way here. The journal wanted us to go the other way, whereas I'm always reading it back the other way. I don't know which makes more sense. 7,000 years to present. At Owen Tarn, okay, just above Mount Owen, or on Mount Owen, it's there. There's a little fire here. No significant charcoal peaks. The stars or the crosses are significant charcoal peaks. Boom, it's gone, okay? And that was well before mining. So it's a myth that mining wiped out the forest, at least in that place. Yeah? And we're looking more into this now and doing a high-resolution thing of this period. Lake Osborne has had lots of fires over the last 6,000 years. As I said, that's an area where ENSO is sort of playing a bigger hand. Fire down, boom, it's gone. Lake Wilkes, plenty of fires, but it's managed to bounce back. So seems to be a really tight correlation between the ability in this data set, and we need to go out and test it more obviously, that if you are in a high probability climate zone, that you are going to be more able to survive burning. Yeah? You have a higher resilience. So this map, if you like, is some kind of pseudo map of resilience for this ecosystem. These are just some other plots about regional climate things. This is basically showing that most of southern Australia is wet and getting drier. Some other proxies doing that, and this is just ENSO moving in. Whether or not it's playing effect over here or not is irrelevant really, because the climate is still quite suitable for recovery there. So our hypothesis here, you can sort of forget about this stuff, is that once ENSO kicks in, in this period here, the climate shifts, moving two of these sites into low resilient zones, whereas the Lake Wilkes site still sits in a high resilience zone, or a suitable climate. So if you like, back to the extinction debt analogy or concept, Owen Tarn, following the onset of ENSO, Owen Tarn and Lake Osborne are sitting in zones of high extinction debt or extinction debt, and fires at those locations have wiped out the rainforest, the Athrotaxis nothofagus rainforest. Whereas at Lake Wilkes, that has not occurred because the climate did not change as much in that spot. And here's just how it's mapped onto that stability landscape, if you like. You've had the ball kicked out, was being able to be kicked out. Okay, there's no doubt that it's still able. They're in zones that are still able to support the montane rainforest, but they've been kicked out of those zones, of that ecosystem. Interesting, Dave. I ran it on Cuprossoides, and you're working in an area that is in a high probability of survival there. So you're barking up the right tree, if you like, where you're doing that restoration work. It may be, and I'll get to this later, this might provide some kind of idea of where is and isn't a good place to put your effort into restoration. Yeah? Do you bank on winners, or do you try and pop up, I don't know, are you Trumpian or are you left wing? I don't know. That's not something for me to think about. I think I'll just provide the information. Well, I can enter the discourse if I want. Okay, so in terms of extinction debt and colonisation credit, what I did was I extracted then from that Max Ent stuff the scores of extant areas of Athrotaxis nothofagus, that community that we're focused on, and plotted a frequency distribution curve. And you can see here that there's a long tail of low resilience. There's a long tail, okay? If you go back to that spatial map, there's a long area of extinction debt, okay, due to the long relaxation time. There's areas of this that are, because since the climate changed around 4,000 years ago, that are now in low resilience space. And this is the location of our two ones that went extinct once they were burnt, okay? This is another site here that we're interested in, here up on the Swallows Nest Lakes, up around that area. It's a high resilience zone, but I know it's been knocked out around there, so we're really interested in testing what's going on there. But the interesting thing here, this big drop-off, is that there is virtually no taking up of high resilience space. Okay, so in this vernacular, it's a high extinction debt and a high colonisation credit. There's no moving of this ecosystem to take up the high resilience zone. Now, is that because the nature of mountains, there's nothing upslope? Is that by geographic barriers? What's going on here? Why isn't the ecosystem moving in to the suitable climate space? Is it something that we can do to assisted migration? Or is it something that's a landscape feature, something I need to dig my teeth into a bit more? But it's a feature of the data. Okay, so then digging into the other factors that we can glean, we've got some paired sites here, Lake Osborne and Lake Perry. They sit right next to each other, 230 metres away from each other. There's some slight topographic differences, but all intents and purposes, they're at the same altitude, got the same vegetation. They're it's almost a perfect experiment, really. So we look at the situation here. Here is time going the way that it should, old to young. Charcoal, significant charcoal peaks here, sort of derived through statistics. And we've identified the ones that occur at both sites, at both Lake Osborne, this one here, and Lake Perry, this one here. And you can see here that this sort of montane rainforest dominates the early Holocene, or the deglacial period. Then, once ENSO sort of starting to get out of bed and really kicks in, you're getting these fires roll through. Okay, but the really interesting thing is here is you get persistence at Perry when you don't get it at Lake Osborne. So we wanted to investigate what's going on here. We're sort of caught between two worlds here. First, I'll take you through topography. I still haven't worked out a statistical test to correlate not that statistics are everything, correlate the time series data with landscape data. But I flew a drone over it, got permission, flew a drone, nearly lost it, it was so windy. Calculated, so it gives me the reason I did it is sort of gives me a 8 centimetre resolution, pixel resolution. Converted it into aspect and slope, and then identified these sort of topographic pyrophugia, steep south-facing slopes, which is what Dave and Sam have identified. And it turns out that there is a significant contiguous area. Overall, the areas are the same. So when I think, what's going on here? But the topographic pyrophugia at Perry are really, really concentrated in one area. Yeah? And I started thinking about this spatial contiguity theory that has been discussed, that mainly in conservation areas, is if you have little parcels, it's not as effective as having a large area with a large core. Yeah? And there's, a distance, especially, and there's people have done the investigation on how far a rainforest, the buffer of a rainforest has. I think I've forgotten what it is. It's in this paper that's just been accepted into JQS. Especially in temperate forest, if they have a distance from the edge to the core over a certain distance, then they're much more resilient to fire or buffered from fire than smaller patches. So our conclusion was here that one of the contributing factors was that this large area of core buffered that site compared to Lake Osborne. And these are both in low resilience spaces here. So there's some local scale potential overriding of the macroclimate, some local micro feature that can override the influence of the macroclimatic change that occurred around 4,000 years ago with ENSO really coming to town. So then we looked at species invasion, and this is pyrophytic taxus, but eucalyptus. I don't know why at this moment I was trying to speak to an audience beyond Australia, I guess. And you can see here at Lake Osborne, after these fires, there's a slight increase in these eucalypts and then a really big one at the end, and it takes over. Yeah. Whereas at Perry, there's nothing. Right at the end here, danger, danger, it's hitting up this sort of threshold, if you like, of what we sort of hypothesised might be too late, and that's that big dip here, corresponding to this fire in the British invasion period. Okay, so I did that superposed epoch analysis again, which is basically a time series test that sort of correlates two time series backward and forward and tries to work out whether they're related. And it turns out that at Lake Osborne, every time there's a fire that drives a negative response in the montane rainforest, there is a significant increase in eucalypt. Yeah? At every one of those. That relationship doesn't occur at Lake Osborne, Perry. So here we have two, either complementary, competing, I don't know, how do topography and the ability of a species to invade or have an influence once it's invade combine to provide this example of a persistence of forest at one site and not at the other, or persistence of species at one site and not at the other. And if you sort of map this, and I like these are, I'll start here, this is ENSO. As I said, it's quiescent, then it sort of starts to ramp up, and then it really comes to play. This is 14,000 years ago to present. This is an ordination of each site, both sites together, boom, in a giant metadata, ran an ordination through, then I pulled them out and extracted the main variants through them. So here, basically, this is the trajectory of vegetation change at Lake Osborne. This is a trajectory of vegetation change at Lake Perry in ordination space. So for those who are with that. So they both do the same thing. They behave really well together. Then I took the DCA scores and did a frequency distribution plot, and they overlap really well. Okay. Then ENSO kicks in, they start to separate, and you can see the DCA scores start to separate. The two systems are becoming a bit distinct from each other. Yeah? And then right here, towards the end, they're really far apart, and that difference is is significant if you do a test on the populations. So you're getting these two are behaving together, ENSO kicks in, they start sort of doing different things, and then they've ended up in different places, yeah? Because of topography and species invasion. Which one's more important? I don't know. And then in terms of sort of they were both sitting in a single basin, another basin starts to appear, Osborne moves out, and then they fully separate, yeah? In terms of that stability landscape stuff. Okay. So then I was inspired by Lydia Cole and Kathy Willis and a few others who just did a grab bag of all pollen records from tropical forests and measured the time it took after every single downturn in forest taxa, every time it took for things to recover, and then they plotted that as a function through time, and they showed that tropical forests were becoming slower through time in their recovery. Yeah. So I did this for the Southern Ranges sites, all of these sites. And you can see here, 10,000 years ago to present, increase in climate variability, that, you know, this is recovery only after fire. So each of these dots is a fire at the records, yeah? And it goes through time. All of these but Lake Perry lose all montane rainforest elements after this period, yeah? They're gone. Lake Perry's surviving. Then I did a sort of rise over run because I didn't know whether that lake there, comparing the actual time it took for recovery at both sites was correct, given the differences in areas. I wanted to be sort of a relative rise over run variation. I can declutter that for you later if you're interested. But basically, you're getting this apparent decrease from the early Holocene, when there was lots of montane rainforest at all of the sites, decrease through time. So basically, these systems are slowing down in their recovery as climate's getting more variable. Yeah, they're slowing down. If you go back to that resilience stuff I was talking about, when you're coming close to a critical threshold or a bifurcation or whatever you want to call it, tipping point, your ecosystem will slow down in its recovery. And that's what this is indicating. High recovery, slow recovery. Cool. So wrapping all this up, the ecology of montane rainforest tree dominance exposes them to risk from fire because of the long relaxation time, which creates a high extinction debt. And we've got data for that now. If you're in disequilibrium with climate, or at the very tail of the equilibrium, the problem with the Maxent thing is because it's based on a modern climate, you can't actually say it's in disequilibrium. But if you're in that long tail of really low probability, which you can argue is in a disequilibrium with climate, then you are low resilience to fire. Climate exerts a first-order control over the resilience of this system, and probably most systems, to disturbance. We've got the neo and paleo data to back this up. Validating the use of the species distribution model climate envelope as a resilience proxy. Sorry, I've got the auto thing through here. Sites of high model inferred resilience recover from burning. Sites of low model inferred resilience are likely to collapse. Topography and species invasion are important secondary controls over the resilience of this system. Okay, topographic fire refugia can facilitate post-fire recovery or protect species from burning. Long-term climate has eroded the resilience of this forest type. Critical slowing down has occurred in response to ENSO. So where to with this knowledge, and I guess this is where I'm interested in taking it, but I'm severely undergunned, I think, in terms of the socio-ecological context, is where should we then allocate our resources? There's only a finite amount of money. It's a bloody hard place to put out fires. Yeah? Should we bank on the high resilience zones to recover and then triage the low resilience zones, thinking they'll be right? Or do we think climate's going to continue to change, and the next step we're doing with this now is bioclim's been forward casted, if you like, and we're going to apply the model under a climate change scenario to see what happens to that space and sort of subtract one from the other to show the potential direction here? Or do we forget about the low resilience areas and work at buffering further the high resilience zones? And that's something I think that from my view, should be a conversation point moving forward before. Otherwise, we're just sort of in this space of chasing our tails, if you like, rather than being forward planners. All right, that's it.
Are there any questions for Michael?
Yep.
The Tassie Climate Futures technical report, I think it's figure 6.89 thereabouts. It projects the quarterly rainfall across all of Tasmania going forward, right, basically through to the end of the century. It shows a distinct increase in winter rainfall and a very distinct decrease in summer rainfall. Have you looked at how those model changes fit into your bioactive models and suggest what areas basically become completely not habitable for these species?
Yeah, it's a good question. It'd be interesting to do. I think that under the current, if you're modelling based on the current relationships, the seasonal distribution of rainfall is down the rank end that's important to the model. How that then will come out in the Maxent terms of using those, I'm not sure. But maybe there's some other kinds of modelling that can be done that can do that. Anecdotally, that SAM relationship is spring-summer rainfall. So if you get a negative, then you're going to get more fires. So anecdotally, that will increase fires, irrespective of winter rainfall. It doesn't matter. It's always wet in winter here. It's the dry season, or just prior to dry season rainfall that's the important one. So
Just as a sort of secondary code of that, with the concurrent increase in temperature, how the warmer, wetter winters affect the relative growth of invading species compared to the...
yeah, well, the invading species here is eucalypts, I guess we're talking about. So I'm not.
Yeah.
Yeah, I don't know. These are all great questions that really can be coupled to the stuff that we've done. Yeah.
Great talk, Michael. Thank you. And as you know, we've got some restoration stuff going on up at Lake Mackenzie. I think that last point you made about the where should we target those efforts is really important. And I'm obviously also interested in the what. And at the moment, we're doing trialling things to promote the pencil pines, but we're operating in among eucalypts, often or close by to eucalypts. So I'm just interested in your opinion on whether we need to be looking at controlling the eucalypts as equally important or
Yeah. I guess the first decision is what do you want, And if you want to just get the Athrotaxis back in there with the sphagnum, which I think is what you want, then why not chop them down, If that's what you want, be unashamed about it. I mean, you're manipulating the ecosystem. You can't sort of stick your toes in and pretend it's all natural. Like, get in there and do it. But once again, these questions I'm often asked, how often should we burn, I can tell you what people or think might have happened. The question that needs to be addressed is, what do you want? And if you want to get this system back in, you want to have it, and it's going to be a managed system going forward by the looks of it, then don't hold back, Get in there and do it. I don't know.
I had a question about the graph about, I think it was diatoms versus pollen and the rate of change. How do you calculate that, or what is that?
It's based on the difference between, it's not really an ordination, but basically the difference in a summary of the data between one point and another as a function of time. Yeah, so if you're getting in sort of multivariate space, if you're getting a large distance, chi-square difference I think was the metric we used, as a function of time though, that's the thing. So you've got a...
In numbers?
Yeah. Composition.
Oh.
Yeah.
Might pass me a bit fast, but how can you tell us again how you're using the Maxent scores as a measure of resilience?
I'm not. I'm saying that it's probably... so the Maxent's just telling you where the likelihood of climate is, yeah? What the likelihood of finding the community as a function of climate is. And it just so happens if you're a low probability of finding it in terms of climate and you are burnt, you don't recover. And if you're in a high probability of finding it and you're burnt, it seems as though, from n equals 1, there's a lot of time and effort into these work records, so they take time to accumulate, that you do recover. So as I said, it's kind of like a pseudo-resilience thing. Yeah. But there may be some other factors. Maybe that there's just a different soil type, or I don't know. And that's where we need to populate with more data. But that's where I'm coming at it from.
So you're using that word resilience.
Yep.
These days, in terms of the engineering resilience.
Yep.
Back to where you were before.
Yep. Yep. Capacity to return to where it was.
Yeah, okay. It's sort of different from the Sheffer, Polling, Carpenter, Mason.
Ecological resilience. Yeah. 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 Good point.
Just on that makes sense. I'm sorry, I don't really understand it. So, how do you figure out climate probabilities if you're basing them on the current distribution of the species, but within the current distribution of the species, some of them are already in an extinction debt?
Well, that's that. You can only the problem. There's a lot of literature on this with the forecast and hindcast stuff. With this, you're given what you've got, and that's going to be in various states of shifting. It might work for really fast-living species. They're always occupying and migrating. But when you've got these longer-lived ones, you're going to be in your model. So this is going to probably, given the long tail, it's probably going to underestimate the extinction debt. Yeah. So this is a best-case scenario because you're incorporating things that are in extinction debt as being probable, things that are potentially out of equilibrium with climate in the climate model. But you can't a priori go in and say no, yes. You've just got to run it and then just go with it. Greg?
I'll just follow that and sort of comment more than a question. I just feel that because of the nature of the data you're feeding into the vaccine, it's like presence absence on cells,
Yeah.
and it doesn't account for abundance. It actually probably smooths quite a lot of that out.
Yep.
The error out, so it's actually better than it looks.
Yeah.
So one pencil pie in Lake at Great Lake actually has a massive influence compared to 10,000 at Dixon King.
Yeah. Yeah, no, you're
So
completely
it's
right.
Picking up a lot of the signal because of those rare things.
Yeah. There's all we can do really with the data we've got. There isn't the present abundance. Yeah. No, it's not a perfect system. That's what we've got.
If I could make a comment on behalf of Tim Broderick, there is another way of thinking about this, and that's looking at the physiology of the species. And Tim's, the devastating observation is you can grow Desalma on the east coast of Tasmania. Desalma is restricted to montane environments. Go figure. And, the explanation is that Desalma isn't everywhere because of fire.
Yeah.
Physiologically, it could be pretty well everywhere. And that's like the ultimate vulnerability with these bottling refugial species which are affected by fire, which goes back to Sue's point that you're not actually looking at your sample is fundamentally in disequilibrium.
Yeah, and I'd say, for example, knowing what I know, I would never run this on Largostrobus because every pollen sequence from the last interglacial in Western Tasmania has Largostrobus, but it's found nowhere near there now. So that's an obvious one to me that is the biggest casualty of human arrival. So modelling it just on its current is kind of futile. And it may well be with Aphrotaxis. It's, all these things are kind of wrong. Models are all wrong, aren't they? They're just vehicles for thought. And it just so happens in low probability areas, they're collapsing. In high probability areas, they're not. So it's a very useful, incorrect model.
It's sound. It's just that the prediction is it's got an inherent bias in it. That's the problem.
The point is though that you've got to say all models are wrong. On one hand, I agree, but on the other hand, you're also trying to pose a management response. So that's when it becomes really difficult because you're trying to say to people, okay, and also when you're going to project into the future, people actually end up saying, so what should we do? Where should we restore this? And so we do actually have to move beyond just saying our models are incorrect, and we do need to get better at applying that information to real life.
You'd know better than most. Climate models, we can't even get the modern climate right, but that doesn't erode their utility in running experiments and saying, well, what is this, and they're very useful.
Understanding the limitations is really important. And trying to get them as reflective of the biology and your understanding of the historical and current biology then helps with those decisions. Because otherwise it's about, if
Yeah.
We just say it's up too uncertain.
Yeah.
We're making a decision to do nothing.
Well, you talked about South Island, New Zealand and deforestation now and treating people as if they were intelligent agents. So you said in passing that you're going to look at future modelling. Are you going to try and build people in as intelligent agents to that, those that are modelling to try and think about how can we manage into the future?
Yeah, and that'd be something that I was over, and that guy that David works with a bit, George Perry, that we've been discussing. That's well beyond me, you know. I'm just a guy who digs holes in lakes and counts pollen and charcoal, you know. But definitely moving into that space is trying to get people into the models, yeah. And intelligent people, because you know, and there's a whole another layer here about how that reflects what we actually think of prehistoric, as in history, our history, people, as being unhuman. You know, like outside that overlay, we need to start moving in towards that kind of space. Yeah.
Well, the other problem we have is that there's archaeological materials all through the pencil pine.
Yeah.
So,
but there's a history of a conflation of people and just irresponsible fire. You know, whereas intelligence is big.
yeah,
You know,
so it's really complicated.
Yep.
Did you have one more comment?
No, just that's
Okay, well, I think that's been, Michael will be hanging around afterwards, so thank you very much. It's been really
No worries.